Something unprecedented happened on October 29th, 2025. The interstellar comet 3I Atlas reached its closest point to the Sun, and in those critical hours, it did something no natural comet should do. It brightened by a factor of 5, not gradually, not predictably, 5 times more luminous than before, blazing blue against the cosmic darkness. The data arrived between October 31st and November 4th from observatories worldwide. Scientists cross-checked the numbers. The brightening was real, but here's what troubles them. With that kind of increase, 3I Atlas should have lost at least 13% of its mass. Comets brighten when ice turns to gas, when their frozen cores evaporate under solar heat. More brightness means more material ejected into space. It's basic physics. A natural comet gaining this much luminosity would shed a massive cloud of gas and dust, a halo visible to every telescope pointed in its direction. Yet, when astronomers searched for that cloud, they found something deeply wrong. The preliminary post-perihelion images show no evidence of the massive gas envelope that should be there, no vast coma, no debris field matching the scale of brightening. If 3I Atlas follows natural laws, it expelled 13% of its body in a matter of days. Where did all that material go? The mathematics are straightforward. Harvard astronomer Avi Loeb calculated the mass loss based on momentum conservation. For a comet to accelerate without gravity pushing it, it must throw material in the opposite direction, like a rocket burning fuel. The force detected on 3I Atlas translates to a specific amount of mass that had to leave the nucleus. At thermal speeds, meaning the normal temperature-driven evaporation of ice and gas, the comet would need to lose more than 13% of its total mass. But if something else caused the acceleration, something expelling material at higher velocities, then far less mass would be required. That's the paradox. Either we're missing a colossal gas cloud that physics says must exist, or the acceleration came from a source that doesn't behave like sublimating ice. Then there's the second Atlas comet, C2025 K1 Atlas. Not from another star system, but from the Oort cloud at the edge of our solar system. It reached perihelion 3 weeks earlier, on October 8th, diving to within 31 million miles of the Sun. Experts predicted it would disintegrate. Most comets making such a close pass get torn apart by gravitational stress and solar radiation. C2025 K1 should have become a streak of vapor and fragments. It survived. Not only survived, but transformed. Astrophotographer Dan Bartlett captured it from June Lake, California, and the image shows something rarely seen in cometary science. The comet glows gold. Not white, not the familiar green of carbon emissions, not blue from ionized gas. Gold, a warm metallic sheen, coating its tail as if the sun had alchemized its surface. Comets reflect sunlight through their dust and emit colors based on their chemical makeup. Green comes from dicarbon molecules. Blue emerges from ionized carbon monoxide. Red can indicate organic compounds. But gold, that requires something specific. It means an absence. Spectroscopic analysis from the Lowell Observatory in Arizona confirms what the color suggests. C2025 K1 Atlas is severely depleted in carbon-bearing molecules. Dicarbon, carbon monoxide, cyanide, the compounds found in virtually every known comet, exist in trace amounts only. In the entire catalog of observed comets, only 2 others have shown this level of carbon depletion. The odds of encountering a third are vanishingly small. When carbon compounds are missing, the remaining dust reflects sunlight differently. The result is that golden hue, that strange metallic glow. Scientists openly admit they don't know exactly why this comet lacks carbon. It should have formed from the same primordial material as other Oort cloud objects. Its composition should mirror its siblings, but it doesn't. Both comets carry the Atlas name. Both defied predictions. The interstellar visitor brightened impossibly without the expected gas release. The solar system native survived a death sentence, and emerged chemically wrong. October 8th and October 29th, 3 weeks apart, two perihelia, two objects that refuse to behave. The U.S. government has gone silent. NASA's normal flow of data and imagery stopped when the federal shutdown began on October 1st. The usual stream of observations, the detailed reports that follow significant astronomical events, ceased. On October 31st, Congresswoman Anna Paulina Luna sent a formal letter to NASA's acting administrator demanding the release of records, images, and data related to 3I Atlas. She called the information critical to understanding interstellar visitors and their interaction with our solar system. NASA scheduled a call with her for November 6th, nothing sooner. In the meantime, the All-Domain Anomaly Resolution Office, the Pentagon division created to investigate unidentified phenomena, issued a statement. They're monitoring reports closely, but consider 3I Atlas outside their jurisdiction. It's assessed as a comet, therefore not an unidentified anomalous phenomenon. Not their problem. But if it's just a comet, why does it violate the models? Why does one burn gold without the elements that should define it? And why does the other shine 5 times brighter without scattering the mass that physics demands? Loeb calls this a potential black swan event. Most likely natural, he says, but the anomalies are significant enough that we must consider other possibilities. The implications, if this is anything other than a comet, would be profound for humanity. Between November 27th and January 27th, the International Asteroid Warning Network will conduct a dedicated observation campaign. Telescopes around the world will focus on 3I Atlas as it moves away from the Sun, finally emerging from the solar glare that has obscured it. They'll measure its composition with spectroscopy, track any further acceleration, search for that missing gas cloud. C-2025 K1 Atlas will make its closest approach to Earth on November 24th, passing just 37 million miles away. Backyard telescopes will be able to see it, that strange golden ribbon rippling through space. 2 comets, 1 name, and something neither of them should be doing. The non-gravitational acceleration is what changes everything. When the latest orbital calculations came through on November 5th, they confirmed what had been suspected, but not yet proven. 3I Atlas is pushing itself. Not much, but enough to measure, enough to matter. The acceleration breaks down into 2 components, both lying in the comet's orbital plane. There's a radial push away from the Sun, and a transverse force perpendicular to that direction. No vertical component exists, nothing pushing the comet up or down relative to its orbit. Just these 2 forces, precisely in plane, acting like controlled thrust. The measurements stand at 3.7 standard deviations above background noise. In statistical terms, that's solid. Not overwhelming, not unquestionable, but significant enough that dismissing it requires ignoring data. The acceleration was normalized to 1 astronomical unit, the Earth-Sun distance, to account for the changing solar radiation pressure at different distances. Even with that normalization, the forces remain detectable. Natural comets do show non-gravitational acceleration. When ice sublimates into gas, it jets away from the surface, creating tiny rockets that nudge the nucleus in various directions. This is expected. This is normal. But those forces appear erratically, coming from multiple vents across the surface, pushing in different directions as the comet rotates. The accelerations vary. They're chaotic. What 3I Atlas displays is different. The forces maintain consistent directions. They align with the orbital geometry, and critically, they require that massive gas release to function through natural means. Between July and September 2025, astronomers analyzed 4,022 data points from 227 observatories worldwide. During those 3 months, 3I Atlas showed no non-gravitational acceleration whatsoever. 0. The comet moved through space following pure gravitational trajectories, responding only to the sun's pull and the faint tugs of planets. Then it approached perihelion, swung around the sun, and suddenly these forces appeared. Something switched on. The gas composition adds another layer. In October, spectroscopic observations revealed that 3I Atlas contains far more nickel than iron. That ratio is backwards. Every known comet, every asteroid, every rocky body in the solar system shows more iron than nickel. It's fundamental to how planets and small bodies form. Iron is more abundant in stellar nucleosynthesis. When stars forge elements and scatter them into space, they produce more iron. The material that collapsed into our solar system 4.5 billion years ago had that same ratio. Everything born here should reflect it, but 3I Atlas doesn't. Its nickel to iron ratio resembles industrially produced nickel alloys, the kind humans manufacture for specific purposes: high temperature resistance, corrosion protection, structural integrity in extreme conditions. Then there's the nickel to cyanide ratio, orders of magnitude higher than any observed comet, including 2I Borisov, the second interstellar visitor we detected back in 2019. Cyanide is common in comets. It forms naturally from carbon and nitrogen in the cold depths of space. Finding abundant nickel but relatively little cyanide inverts the expected chemistry. The water content is equally strange, only 4% by mass. Comets are typically described as dirty snowballs, huge chunks of ice mixed with rock and dust. Water dominates their composition. It's what makes them comets rather than asteroids. But 3I Atlas is dry. It has some water, enough to confirm its outgassing, but nowhere near the levels that define cometary bodies. 4%. That's closer to an asteroid's moisture content. Yet it has a tail. It brightened dramatically. It's shedding material. The polarization measurements are unprecedented. When light scatters off a comet's dust, it becomes polarized, with the electric field waves oscillating in preferred directions. The degree of polarization tells us about the dust particle sizes and composition. Every comet measured shows positive or mildly negative polarization, depending on the viewing angle. 3I Atlas shows extreme negative polarization. Nothing else does. Not 2I Borisov. Not any solar system comet in the catalog. The light bouncing off its dust is polarized in a way that defies the standard models. Scientists calculate the probability of this occurring naturally at below 1%. Below 1% doesn't mean impossible. It means rare, exceptionally rare. And when you start stacking these rarities together, when you accumulate anomaly after anomaly, the compound probability drops further. Nickel over iron, nickel over cyanide, 4% water, extreme negative polarization, no gas cloud despite massive brightening, non-gravitational acceleration appearing only at perihelion. Each individually could be explained away. Together, they form a pattern. The trajectory presents its own puzzle. 3I Atlas entered the solar system on a retrograde orbit, moving opposite to the direction planets travel. That's not impossible for an interstellar object, but its orbital plane aligns with the ecliptic to within 5 degrees. The ecliptic is the flat disk where planets orbit. Most objects coming from random directions in interstellar space would cross that plane at steep angles. They'd come in from above or below, diving through at wild inclinations. But 3I Atlas glides along nearly parallel to it. The probability of that alignment occurring by chance sits at 0.2%. 1 in 500. Could happen. Rare, but possible. Its arrival time also raises questions. The comet's trajectory brought it within tens of millions of kilometers of Mars, Venus, and Jupiter. Not collision courses, but notable approaches. And its perihelion occurred when Earth's position made direct observation impossible. The sun blocked our view during the critical passage. If you wanted to visit the inner solar system while minimizing detection, while getting close looks at multiple planets. This trajectory would serve that purpose. The probability of such a path occurring randomly: 0.05%, 1 in 20,000. Avi Loeb has been documenting these statistical anomalies since the comet's discovery. He's careful to emphasize that low probability doesn't prove artificial origin. Unlikely events happen. The universe is vast. Strange coincidences emerge naturally. But he also notes that dismissing the possibility requires ignoring the data. Science advances by considering all hypotheses that fit the observations, not just the comfortable ones. The upcoming observation campaign will test the natural comet hypothesis directly. If 3I Atlas is natural, then the post-perihelion period should reveal that missing gas cloud. 13% of its mass had to go somewhere. The cloud should be expanding, glowing, detectable across multiple wavelengths. Spectroscopy will identify the molecules. Imaging will show the structure. If the cloud isn't there, if the observations show no evidence of massive outgassing matching the brightening and acceleration, then the natural explanation fails, not becomes unlikely. Fails completely. And if that happens, what remains? The size comparison tells its own story. 3I Atlas is massive, roughly 1,000,000 times more massive than Oumuamua, the first interstellar visitor we detected back in 2017. 1,000 times heavier than 2I Borisov, and it's moving faster than both of them. That combination is statistically improbable. Large objects typically move slower. They form in more stable environments, gather more material, and don't get ejected from their home systems with extreme velocities. Small objects get kicked out easily. A gravitational interaction with a giant planet can fling a small rock into interstellar space at high speed. But moving something the size of 3I Atlas requires more energy. Much more. The probability of an interstellar object being this massive while moving this fast, less than 0.1%. And yet, here it is. The third interstellar object ever detected, breaking the pattern set by the first two. There's another detail buried in the Hubble Space Telescope observations from July. The images show a teardrop-shaped structure around the nucleus, a cocoon of dust streaming away from the solid core, but they also reveal something else: a jet, pointing sunward. Comets don't do that. When a comet approaches the sun, solar radiation heats the side facing our star. Ice vaporizes, gas erupts, and the resulting jet pushes away from the heat source. Always away. The gas and dust stream in the direction the pressure pushes them, which is outward from the sun. That's why comet tails always point away from the sun, regardless of the comet's direction of travel. But 3I Atlas displayed a jet aimed at the sun. Not an optical illusion, not a geometric perspective trick. The analysis confirmed it was real. Between July and August, material was actively moving toward the sun from the comet's nucleus. Natural explanations exist. Comets have complex shapes, uneven surfaces with cliffs and craters. A vent on the night side could eject material that then curves around the nucleus, appearing sunward from certain angles. Rotational effects could create unusual patterns. These aren't impossible scenarios, but they're additions to the growing list. Another anomaly requiring special circumstances. Another coincidence. Meanwhile, C2025 K1 Atlas continues its own performance. The Golden Comet, the Survivor, the chemically depleted oddity. After perihelion, it should be fading. Comets are brightest near the sun. As they retreat into the outer solar system, their activity dies down. The surface cools. Sublimation slows. They dim. C2025 K1 has reached magnitude 9, matching 3I Atlas in brightness. For an object that barely survived close solar passage, that sustained luminosity is unexpected. It's not brightening further, but it's not fading at the expected rate either. Something about its interaction with solar radiation maintains its visibility. The carbon depletion may be the key. With fewer volatile carbon compounds to sublimate early, perhaps the comet retains more material than expected. It burns differently. The solar wind strips away the outer layers, but what remains reflects light efficiently. That golden dust, whatever its composition, catches sunlight and holds our attention. Two comets, both at magnitude 9, both accessible to amateur astronomers with modest telescopes. The interstellar visitor and the Oort cloud wanderer, separated by origin, but united in strangeness. Both discovered by the same telescope system. Both defying expectations at perihelion. Both brightening when they shouldn't. Surviving when they shouldn't. Displaying chemistry that doesn't match their supposed origins. The Atlas telescope network was designed to detect near-Earth asteroids, objects that might pose impact threats. It scans the sky continuously, looking for motion against the background stars. It's not looking for interstellar objects or unusual comets. It's looking for danger, and it found these two. The timing matters. C2025 K1 discovered in May 2025. 3I Atlas discovered in July 2025. Perihelion on October 8th and October 29th, 3 weeks apart, both carrying the Atlas designation, both emerging from the telescope network's automated detection algorithms within months of each other. That's not suspicious by itself. Atlas discovers objects regularly. It's doing its job, but finding two such anomalous comets in rapid succession, both with characteristics that challenge our understanding, both requiring multiple explanations to fit into natural frameworks, raises a question. Are we witnessing something unprecedented in modern astronomy? A year where the cosmos decided to send us puzzles instead of predictable ice balls? Or is something else happening? The scientific community remains largely cautious. Most astronomers working on these objects favor natural explanations. Comets are complex. They form in different environments. They undergo processing during their lifetimes. Radiation from cosmic rays, impacts from debris, gravitational perturbations, all these factors modify cometary surfaces and interiors over millions or billions of years. 3I Atlas spent eons in interstellar space before arriving here. Cosmic rays bombarded its surface. High-energy particles altered its chemistry. It's been transformed by billions of years in the void between stars. Of course, it looks different from solar system comets. Of course, its composition is unusual. C2025 K1 formed at the edge of the solar system, in the coldest, most distant reaches of the Oort cloud. That environment differs from the regions where most comets originate. Maybe objects from that zone naturally lack carbon. Maybe we simply haven't observed enough of them to know the full range of possibilities. These are reasonable arguments. They acknowledge the anomalies while providing natural frameworks to understand them. They don't require invoking extraordinary explanations, but they're also cumulative. Each anomaly needs its own special circumstance. The trajectory requires one explanation. The composition requires another. The acceleration requires a third. The timing requires a fourth. Stack enough special circumstances together, and the natural explanation becomes complex enough to rival alternative hypotheses in implausibility. This is where Avi Loeb's black swan framing becomes relevant. Science typically deals with white swans, events we expect, phenomena that fit established theories, observations that confirm what we already know. When we see something unusual, we first try to explain it within existing frameworks. We should. That's good science. But occasionally, we encounter black swans, events so rare, so unexpected, that they force us to expand our frameworks. Continental drift was a black swan. Plate tectonics defied the static Earth model geologists had assumed for centuries. Quantum mechanics was a black swan. Subatomic particles, behaving as both waves and particles, violated classical physics. Black swans don't announce themselves. They look like anomalies at first, like mistakes, like measurement errors. Only when the evidence accumulates, when multiple independent observations confirm the strangeness, do we recognize that we're seeing something genuinely new. Are these comets black swans? Or are they just unusual white swans that happen to share unusual characteristics? The observations between November 27th and January 27th will move us closer to an answer. When 3I Atlas emerges fully from the sun's glare, when instruments can study it without interference, the missing pieces will either fall into place or the mystery will deepen. And C-2025 K1 approaches its closest point to Earth in 3 weeks. November 24th. Thanksgiving week. That golden ribbon in the sky, visible to anyone with binoculars and clear weather. 2 Atlas comets, 2 dates, 2 questions without answers. There's one more detail about 3I Atlas that hasn't received much attention outside specialized circles. Its arrival direction. The point in the sky from which it came before entering our solar system. In August 1977, a radio telescope at Ohio State University detected a powerful narrowband signal from space. It lasted 72 seconds, far stronger than background noise, with characteristics suggesting intelligent origin. The astronomer reviewing the data was so stunned he wrote, "Wow," in the margin of the printout. The signal never repeated. Decades of searching that same patch of sky yielded nothing. The wow signal came from the direction of the constellation Sagittarius, near the Sagittarius-Scorpius border. Astronomers have debated its origin ever since. Natural explanations exist. Passing comets can emit hydrogen line radiation at the same frequency. Terrestrial interference could have caused it. But no definitive answer emerged. 3I Atlas arrived from a direction that coincides with the wow signal source to within 9 degrees. 9 degrees isn't precise. It's roughly 18 times the width of the full moon. That's a significant patch of sky, but it's also not random. The probability of an interstellar object arriving from that general region by chance. 0.6%. Does this mean 3I Atlas is connected to the WOW signal? No. Not necessarily. Not even probably. But it adds to the list. Another low probability occurrence. Another data point that wouldn't be remarkable alone, but becomes interesting when combined with everything else. If you were designing a probe to visit another star system, what would you want it to do? Survey the planets. Measure their properties. Approach close enough to gather detailed data, but not so close as to be destroyed by gravitational forces, or detected easily. You'd want it robust, built to survive the journey through interstellar space. You'd make it from materials that resist radiation damage and temperature extremes. Nickel alloys fit that requirement. They handle thermal stress well. They don't corrode easily. They're stable across wide temperature ranges. If an advanced civilization sent a probe through the galaxy, nickel alloys might be part of its construction. You'd also want the probe to be efficient with resources. Carrying massive amounts of fuel across interstellar distances is impractical. Light sails, ion drives, or other low-thrust propulsion systems make more sense. You'd activate them only when necessary, conserving energy during the long cruise phase. When approaching the target star, you'd need propulsion for course corrections, orbital adjustments, controlled maneuvers. That matches the acceleration pattern. None during the approach. Activation near perihelion. Forces aligned with the orbital plane, suggesting directional control rather than random outgassing. The water content also fits. A probe wouldn't need to be made of ice. It might have some water for cooling systems, or as reaction mass for thrusters, but the bulk would be structural materials and instruments. 4% water makes sense for technology. It doesn't make sense for a comet. This is speculation. It's building a narrative from anomalies. Scientists rightly resist this kind of reasoning. Data points don't prove hypotheses. They suggest possibilities. The natural comet explanation still holds for each individual observation if you grant enough special circumstances. But consider the alternative framing. If someone showed you an object with all these characteristics and asked you to identify it without knowing the context, what would you conclude? Nickel-rich? Water-poor? Minimal carbon? Extreme negative polarization? controlled acceleration appearing on schedule, trajectory aligned with planetary orbits and timed to minimize Earth observation at critical moments. Would you immediately think comet? Or would you think something else? The government's silence matters more than it might seem. NASA has observed thousands of comets. When something interesting happens, they release data. Images appear on official websites. Press releases go out. Scientists give interviews. The public gets informed. With 3i Atlas, that flow stopped. The shutdown provides convenient cover. Agencies close, data release halts, and everyone accepts it as bureaucratic dysfunction rather than policy. But Congresswoman Luna's request specifically asked for scientific data critical to understanding interstellar visitors. That phrasing suggests urgency beyond routine curiosity. And AARO's statement is revealing in what it doesn't say. They're monitoring reports closely. They assess it as a comet, therefore not UAP. Therefore not their jurisdiction. But if they're monitoring closely, they've seen the same anomalies everyone else has seen. They know the statistics. They understand the implications. Saying it's a comet because it looks like a comet is circular reasoning when the question is whether it actually is a comet. We don't investigate it because we've determined it's natural, presumes the answer to the question that should be investigated. This could all be procedural caution. Government agencies move slowly. They follow protocols. Interagency communication requires formal channels. The shutdown genuinely disrupts operations. None of this proves conspiracy or cover-up. But it does mean that independent verification matters more. The International Asteroid Warning Network's observation campaign becomes crucial. Scientists outside government control, using instruments distributed worldwide, gathering data that can't be suppressed or delayed. Between November 27th and January 27th, we'll have answers. Not speculation, not statistical arguments, not dueling interpretations of indirect measurements. Direct observations of 3i Atlas at multiple wavelengths, from multiple locations, by multiple research teams. If the missing gas cloud appears, if spectroscopy shows natural comet chemistry, if the acceleration can be traced to specific outgassing vents on the surface, then the natural explanation wins. The anomalies were real, but explicable. We learned something about the diversity of comets. Science advances. If the cloud doesn't appear, if the acceleration continues without corresponding gas release, if the composition remains incompatible with natural formation, then we face something unprecedented. Not proof of artificial origin, but failure of natural explanation. And when natural explanations fail, we must consider alternatives. C2025 K1 Atlas might be key to understanding its interstellar counterpart. If both objects share the carbon depletion, if both show unusual metal ratios, if both display characteristics inconsistent with typical comets, then the shared Atlas name becomes more than coincidence. It becomes a pattern. One golden comet from our solar system's edge, one blue-bright visitor from another star, both appearing in the same year, both found by the same detection system, both presenting chemistry and behavior that challenges models. Amateur astronomers worldwide are tracking both objects now. Telescopes in backyards, on rooftops, at university observatories. Hundreds of independent observers gathering images, taking measurements, sharing data online. That distributed network provides resilience against information control. The data exists beyond any single institution's ability to manage. November 24th will be significant. When C2025 K1 makes its closest approach to Earth, it will be at its brightest and most accessible for detailed study. If patterns emerge, if new anomalies appear, the amateur network will detect them. And then the professional instruments will confirm or refute. Then NASA will need to respond, shutdown or no shutdown. Then The scientific community will need to reconcile observations with theories. 20 days until C-2025 K1's close approach. 22 days until the intensive observation campaign begins for 3I Atlas. Less than a month until we know whether these are extraordinary comets or something else entirely. The universe has sent us two messengers, both named Atlas, both defying our expectations, both carrying questions we're only beginning to formulate. What they're telling us depends on what we're willing to hear. History has taught us to be skeptical. The cosmos has fooled us before. Pulsars were briefly considered artificial beacons until we understood them as rotating neutron stars. The Viking landers seemed to detect life on Mars until contamination and chemical reactions explained the results. Oumuamua sparked speculation about light sails until tumbling rotation and outgassing provided natural mechanisms for its acceleration. We've learned not to jump to extraordinary conclusions. We've trained ourselves to exhaust mundane explanations first. This discipline serves science well. It prevents us from mistaking ignorance for discovery, from confusing the unknown with the unknowable. But that same discipline can become a trap. When we encounter something genuinely unprecedented, our insistence on familiar explanations can delay recognition. The question isn't whether to be skeptical. It's whether our skepticism serves discovery or prevents it. With these two Atlas comets, we face that question directly. The data exists. The observations are real. 3I Atlas brightened fivefold at perihelion without producing the gas cloud that physics requires. It displays non-gravitational acceleration that appeared only when needed, aligned with orbital geometry, suggesting control rather than chaos. Its composition inverts natural ratios, showing more nickel than iron, more nickel than cyanide, presenting chemistry that resembles industrial alloys more than cosmic ice. C-2025 K1 Atlas survived temperatures and stresses that should have destroyed it. It transformed into something rare, something golden, something chemically depleted in ways that only two other comets have ever shown. It maintains brightness when it should fade, defying the expected trajectory of cometary behavior. Both objects share a name, a discovery system, a timing that places them in our sky within months of each other. Both present anomalies that individually stretch natural explanations and collectively challenge them. The natural comet hypothesis requires multiple special circumstances. Each anomaly needs its own rare condition. The trajectory needed to be aligned just so. The composition needed to be processed by billions of years of radiation. The timing needed to be coincidentally synchronized. The acceleration needed to emerge from hidden vents we haven't detected. The missing gas cloud needed to be overlooked by every telescope that searched for it. Possible? Yes, each individually. But when you compound probabilities, when you multiply one rare event by another, the combined likelihood drops. At what point does the accumulation of special circumstances become less plausible than alternative explanations? This is the uncomfortable question. Not whether aliens exist, not whether they visited us, but whether our commitment to natural explanations has become so strong that we'd reject obvious evidence if it appeared. If an interstellar probe did exist, what would we expect to see? It would need to survive the journey, so robust construction from durable materials. It would need to be efficient with energy, activating propulsion only when necessary. It would survey planets, approaching them for data while minimizing detection risk. It might carry minimal volatiles, just enough for thermal management and reaction mass. That description fits 3I Atlas better than the comet hypothesis does. And C-2025 K1, perhaps it's exactly what it appears to be. An unusual but natural comet from the Oort cloud, chemically distinct from typical objects, surviving perihelion against predictions through sheer structural integrity. Its golden color, its carbon depletion, its sustained brightness, all explicable through rare but natural processes. Or perhaps its discovery 3 months before the interstellar visitor isn't coincidence. Perhaps two anomalous objects sharing the Atlas name and defying expectations in the same year means something. Perhaps one golden messenger from our system's edge and one blue messenger from another star represent a pattern we're not yet ready to recognize. We don't know. That's the honest answer. We have data that challenges natural explanations without proving artificial ones. We have anomalies that accumulate into patterns without forming conclusions. We have observations that demand attention without yielding certainty. The coming weeks will provide clarity. When C-2025 K1 approaches Earth on November 24th, instruments will analyze it in detail. When the observation campaign begins on November 27th, 3I Atlas will face scrutiny from dozens of telescopes across multiple wavelengths. The missing gas cloud will either appear or its absence will be confirmed. The acceleration will either trace to natural outgassing or remain unexplained. The chemistry will either fit cometary models or continue to defy them. And then we'll know. Not everything, but more than we know now. Enough to move forward with better questions. Whatever these objects are, they've accomplished something remarkable. They've forced us to examine our assumptions. They've revealed the limits of our models. They've demonstrated that the universe still holds surprises, that our catalog of natural phenomena remains incomplete, that the cosmos operates on scales and timelines and mechanisms we're still learning to comprehend. If they're comets, extraordinary comets, then we've learned that objects from interstellar space and from our Oort cloud can present chemistry and behavior far more diverse than our theories predicted. We've learned that our models need updating, that edge cases exist beyond our experience, that rare conditions produce rare results. If there's something else, something we haven't named yet, then we've learned something more profound. We've learned that we're not alone in asking questions, that intelligence might manifest in forms we didn't expect, that the universe contains not just physics and chemistry, but perhaps intention and design. Both possibilities expand our understanding. Both challenge us to think more carefully, observe more closely, remain open to evidence, regardless of where it leads. The night sky has always contained mysteries. Ancient humans saw patterns in stars and imagined gods. Modern humans see patterns in data and imagine natural processes. Both approaches seek meaning in observations. Both try to explain what we see. These two Atlas comets have given us new patterns to contemplate. Two objects, different origins, shared strangeness. One golden, one blue. One from our solar system's edge, one from the space between stars. Both discovered by automated systems looking for danger. Both arriving when our instruments could detect them, but not immediately explain them. They're still out there right now, moving through space, reflecting sunlight, carrying whatever secrets their composition and behavior encode. Amateur astronomers are photographing them tonight. Professional telescopes are tracking their positions. Instruments are measuring their emissions. Data is accumulating. In 20 days, C-2025 K1 will pass Earth at its closest. In 22 days, the intensive campaign to study 3I Atlas begins. In the weeks and months that follow, papers will be published, debates will unfold, theories will be tested against observations, and we'll be closer to understanding what these messengers, these heralds, these anomalies, truly are. Two comets named Atlas. Two mysteries wrapped in data. Two invitations to question what we think we know about the universe and our place in it. The answers are coming, whether we're ready for them or not.